Our next speaker is Dr. Elizabeth Reilly. She's a senior staff scientist at Johns Hopkins University Applied Physics Laboratory. She's a senior math researcher in complex systems and AI for science at the Johns Hopkins Applied Physics Lab. And she leads applied research projects and teams at the intersection of AI, climate change, materials, neuroscience, and many, many more. So thank you so much for coming, Elizabeth, and please join me in welcoming Elizabeth to the stage.
All right, thank you, Kyle. All right. So good morning, everybody. Happy to be here with you today. As Kyle mentioned, I'm here from the Johns Hopkins Applied Physics Lab, or APL. When you hear me say APL, that's what I'm referring to. And I'm going to tell you about some of our exciting research in artificial intelligence and remote sensing, focusing mostly on the climate data piece here. But I think that a lot of the challenges and potential impacts that we see in the climate space also apply to energy applications and related things. I also want to make sure, before I move on, I acknowledge all my incredible colleagues here who are leading and executing a lot of the work that I'm going to talk about today. And then also want to point out my email address here. I do have an early flight today, so I won't be hanging around too long, but I love talking to people about our exciting research. So please reach out if you want to follow up, or if you want to get involved with APL. I would love to talk to you. So I want to give just a brief background on who we are here at APL, so you understand a little bit the perspective that we're coming from here. We're a division of the Johns Hopkins University. We're a university-affiliated research center, or a UARC. At this point, we have over 8,000 staff, mostly in STEM fields. And we were actually founded back during World War II when some Hopkins researchers were approached by the Navy to work on some guided missile system research. And this ended up being a real differentiator for us in the war. From there, we've kind of expanded to other government sponsors as well as organizations beyond that, always focusing on critical contributions to critical challenges. So something that we've really, a critical challenge we've really dove headfirst into more recently in the past several years is climate change, which we all know has broad impacts for our nation, but also our world. Those areas that we focus on are things like climate intelligence. So how do we get the data, algorithms, information that we need to make decisions in this new climate changed world? But there's also operational resilience, new operational challenges, as well as green systems, so developing new green technologies or thinking about the life cycle of those technologies. What I want to focus on today is three topics, three different projects where we're bringing remote sensing and artificial intelligence to the challenges that we're thinking about. So thinking about transformative impact broadly, things like reaching for global coverage, addressing new operational needs, and predicting the unseen. And then across each of these, I think that one theme that you'll see thinking about remote sensing and artificial intelligence is that it's often not just remote sensing that's being brought to these challenges. It's often bringing remote sensing paired with other model data or other data sources or physical constraints that really brings out the power of remote sensing in these cases. Okay, so the first project I want to cover here is reaching for global coverage, where we are working as part of the Climate Trace Coalition that Jeremy introduced for us to estimate road transportation emissions. Now, Jeremy gave a really great introduction to Climate Trace, but I want to start out by just highlighting how complex this problem is of estimating greenhouse gas emissions from every sector around the world. People often kind of think about their quote unquote favorite sector, right? They focus on transportation or energy or agriculture. But it's actually all of these different areas, industry, mining, wildfires, et cetera, all of these different pieces that together are causing climate change. And we need to reduce them all to get to net zero. Okay, and so this is what Climate Trace, as Jeremy mentioned, is bringing transparency to greenhouse gas emissions tracking across all of these sectors, estimating greenhouse gas emissions so that we can track our progress and identify where more attention is needed. At APL, we're tackling the problem of road transportation emissions. So in the US in particular, the transportation sector is about 27% of our greenhouse gas emissions, which is a huge piece of our emissions. And of course, road transportation makes up the majority of that. When you think about this problem, though, it's a very challenging one. There are so many individual emitting entities, many, many vehicles, over 1 billion vehicles all around the world. So how do we actually track emissions from these? So the way that we tackle this is bringing together satellite imagery, the Sentinel-2 data that Jeremy mentioned, as well as OpenStreetMap road network data to estimate road activity on individual road segments in major cities around the world. So you end up getting a picture similar to this one. This is the DC region. You can see this red circle around the city is the Beltway, if you're familiar with that area. It's pretty much never pleasant to be on. Just bright red. And so this is, we're able to actually make road activity estimates at this road segment level, which we can then pair with emissions factors to get emissions estimates for the roads and the cities. Before I move away from this, I want to just go back to that reaching for global coverage aspect. I love that Kyle brought up domain adaptation at the beginning of this, because whenever you start thinking about a solution that scales up to the world, the entire globe, you have to be really careful about how you apply your methods in areas with different cultures and economic situations and things like that. And this area of road transportation emission is no different. There are different car cultures everywhere, and so we have to be careful about how we extend our methods. Okay, the next topic I want to talk about here is addressing new operational needs, so the potential impact as new operational needs arise. And here I'm going to talk about sea ice prediction. We have two efforts here. One is in predicting sea ice extent, and the other is in predicting sea ice drift, so focused more on the motion. So, as climate change progresses, we're seeing a lot of changes in our climate and our environment. One place that we really see this in a big way is in the Arctic. It's becoming more open. There's a lot more traffic up there. Shipping in the Beaufort Sea, which is the region that is shown here. It's north of Alaska and Canada and the Arctic, has seen shipping increase by a factor of 3 over the last 15 years alone. And so near-term forecasts to help help ships navigate that, the Arctic is becoming more and more important. Right now, the way this happens is the National Ice Center has human analysts. They get a bunch of different remote sensing data sets, and they annotate where the ice is today. However, we still need that forecast of, say, a week ahead that allows us to know if our ship is going to pass through a region safely. So what we did is we took the analyst data, the analyst annotations, the remote sensing data, paired it with weather forecasts to predict where the ice edge would be over the next week. And we're seeing really great results there. In this example that you see here in this image, we were off by maybe like a day or two for the final closing of that passage. The other problem that we're thinking about is sea ice drift, and this gets into the dynamics of sea ice. when you think about the dynamics piece, there are a lot of physical laws that you need to be obeying. And if you are familiar with machine learning and artificial intelligence, there are not typically constraints in place that ensure that you are going to follow those physical laws. Currently, if we're looking at predicting sea ice drift, we're using either heavy computational climate models or on an operational scale. There are other correlation-based methods, but they don't often operate or perform well at the ice edge where we need it to. So our solution uses a physics-informed, neural network, or a PIN, to predict the motion of the sea ice. This allows us to learn from that data that we have, so those training examples, but also from make sure that we are constraining by physical laws and constraints. Okay, so here we used multiple forms of remote sensing data and model data, and then also are looking at the sea ice momentum equation. We're predicting a velocity vector that is an input to this PDE, partial differential equation, that then can be solved to identify the motion of the ice. So the thing I want to point out here is that PINs are actually known to be pretty challenging to train. People are still figuring out the best way to work with them. And pretty much no one is applying them to remote sensing data. PINs are often applied to small fluid dynamics problems. So this is an ambitious approach, but we are starting to see some promising results here that PINs can actually use remote sensing data. The final topic I want to, and potential transformative impact I want to highlight, is predicting the unseen. And I think John said it so well, so I wrote down his quote, and I will say it again. When you make things visible, it drives action. So this is all about making the unseen visible so that we have better situational awareness and can drive action and have impact. All right, so here we're looking at groundwater storage anomalies. For those of you who are not familiar, maybe don't remember your water lessons from back in the day, I'm going to turn this way. The two pieces I want you to pay attention to are surface water here, that's our lakes and our rivers and such. But then there's also this really great resource of groundwater below the water table line there, the saturated zone. Our primary freshwater resource is really the surface water, but when those resources get low, we tap into the groundwater. And in fact, a lot of our irrigation also comes from groundwater. So this, Kyle mentioned the gray satellites earlier, and the gray satellites are actually, I don't understand as much about them as our speaker from yesterday, but I will tell you they're measuring gravitational anomalies of the Earth, and the key piece here is that we're able to pull out terrestrial water anomalies from this data. But this is looking across the entire water column, so not just groundwater, but also soil moisture and snow water and all these other things. So here we need to pair that remote sensing data with a land surface model, GLDAS in this case, to subtract out those other terrestrial water sources and get to the groundwater. And then we can use that to train a convolutional neural network to predict our groundwater storage anomalies. So here is an example of where we are performing a 5-month prediction forward in the Mekong River Basin during a time period where we know there was a drought. So what you can see here is, I'm going to turn this way again. This is our prediction of groundwater storage anomalies in that region over the summer in 2019. This minus 15 centimeters number means that we're expecting the groundwater line to be about 15 centimeters below its baseline for that area. And that's significant because it actually, it takes a while to replenish groundwater storage. This is what the reality was during that time. It was about negative 20 centimeters. And this far right figure shows the difference between the two. So you can tell there are regions where we were off with the intensity, and I think that this was a really good lesson of where we realized we were not incorporating the human aspect here, right? We were looking at things like land surface models and our GRACE data, but we were not bringing in that human withdrawal piece. So we suspect that there was a lot of extra human-based demand here that we're not accounting for. And I think that's something that we see with energy systems as well. So nonetheless, this is a really exciting direction towards making the invisible seen so that we can drive action. All right, thank you.